Okay, we found our basic result that we're going to keep applying in this chapter, and that is very important to remember. If an object is in uniform circular motion on a circle of radius r with a constant speed v, that's what the uniform part means, then it is accelerating, right? Its velocity vector is changing as it goes around, and every time its velocity is changing, there is a non-zero acceleration vector. And so in this case, the direction of that acceleration vector is at every moment toward the circle center. That's why we call it centripetal acceleration. That's the name for the acceleration you have when you're in uniform circular motion. And the magnitude of the acceleration is v squared over r. We're going to get a lot of mileage out of that in this chapter. So, for example, if an object's in uniform circular motion, going around at constant speed v, at one point its acceleration vector looks like this. Here's a later time. Here's a couple more times. The acceleration vector always has the same length, given by v squared over r, always has the same direction toward the center of the circle. Doesn't matter which way it's going around, clockwise or counterclockwise. Okay, let's start out with an elementary, just sort of calculational example, and I'll show you a little trick that we'll get some mileage out of. An astronaut in deep space has a half-kilogram ball attached to a light 0.7 meter long string. She spins it in a circle at a rotation rate of 80 revolutions per minute, and sometimes people abbreviate revolutions per minute as RPM. You've probably seen that before. So we're imagining the string is being held in the astronaut's finger right here, and here's the ball that's 0.7 meters away, and it's going in a circle at a constant speed. And we're not given the speed, we're given this strange RPM thing, so we're going to have to figure out how to wrangle that into a speed. Question A, is the ball accelerating? Well, yes, it's in uniform circular motion. You're accelerating, or an object that's in uniform circular motion is certainly accelerating. Its velocity vector is changing. If your velocity vector is changing, you're accelerating. What is its acceleration? Well, we know the direction. It's toward the center of the circle, so we're interested here in the magnitude of its acceleration. Maybe I should have said that more explicitly. Well, the magnitude of the acceleration is v squared over r, and we know what r is. It's 0.7 meters. So the only challenge here is to find v, and it seems to be related to this 80 RPM that we're given up here. And so we're going to do a little trick, which sometimes I call the distance over time trick. It's not really a trick. It's giving the definition of speed. And that is that if something is moving with a constant speed, we can calculate its speed in lots of different ways. We can watch it for a small amount of time and do the small amount of distance divided by the corresponding small amount of time, or we can let it go for quite a big distance and do the distance it went divided by the corresponding larger time that it took to go that big distance. It doesn't matter which one we use. So when we're calculating the speed, which is exactly what we want for this formula, we're going to try to choose either a distance or a time that's convenient for us in order to help us calculate v. The time that's convenient for us is 60 seconds because look, I know what happens in a minute. It goes through 80 revolutions every minute. So the convenient time for me is a minute. I wrote it in SI units of 60 seconds here. How far does it go? Well, it goes exactly 80 circumference distances, right? And the circumference of a circle of radius r is 2 pi r. So it goes through a distance of 80 2 pi r's in 60 seconds. That's what I call the distance over time trick. Okay, so I can plug in the r that we know, put the numbers in my calculator, and I get 5.86 meters per second, and then throw that into this formula along with the r that we know, 0.7 meters. Again, as usual, I'm going to do this a lot this semester. I'm not putting in the units in the intermediate calculations because I know in the back of my head if I put all SI units in, then I'm going to get SI units out, and I know the SI units for acceleration are meters per second squared, so I'm just going to put everything in SI units, calculate it, and then slap a meters per second squared on the end of the number. So I get 49.1 meters per second squared for the ball at any point along its trajectory. Part C, what is the string tension that causes the acceleration? Well, yes, if the string weren't pulling on it, the ball would be going in a straight line. The string is what's causing it to move in a circle and causing it to accelerate, right? Because it's the only force acting on the ball, and by F net equals ma, that must be that force that's causing the acceleration alone. So in order to find a force, of course, if I know the acceleration, and now I know the direction and the magnitude of the acceleration at, say, the moment that's pictured up here, then I can use F net equals ma to conclude what F must have caused it. Okay, so let's do that. I'm going to use the sum of the force x components equals max. What does x mean? Well, I need to put some axes on my diagram to know that. So what I'm going to do is, the free body diagram's not very interesting here, but I sort of said, at this instant, I'm going to redraw my object up here for a free body diagram. The only force on it is the string tension from the string, which is pulling on it in the only way a string can, which is along the direction the string is aligned. And I'm going to choose my plus x-axis to be toward the center of the circle, in other words, along this direction, and apply the sum of the force x components equals max. Why did I choose that direction? Because that's the direction of the acceleration. We always want to choose one of our axes to be aligned with the acceleration direction if we know it. Okay, so sum of the force x components, well, there's only one force, and it's all along x, so it comes in with a plus sign. The only force is t, that unknown tension. That's what we want to solve for, so it's kind of our variable here. And that's equal to the mass of the object in the free body diagram. Here I didn't label it, but it's a 0.5 kilogram ball, times its acceleration x component, and we already know that centripetal, or its acceleration, is pointing towards the center of the circle, which is all along x. So all I need to do is use the magnitude of the acceleration, and that would give me the x component of the acceleration. The y component would be 0, if I took y to be in the direction tangent to the circle. We don't really need that here. So multiplying my m times a together, I get 24.6 newtons. So that's the tension in the string. Okay, that's a simple example because there's only one force that's causing the acceleration. But things aren't always going to be that simple. Let's start thinking about other more complicated situations. What other kinds of forces besides string tension can serve as the cause of uniform circular motion? Well, there are lots of them. Anything that pulls on something and keeps it going in a circle could do that, including gravity, right? If you think of, imagine, we know the Earth's, at least from certain inertial reference frames, is going to be moving, but if we sit next to the Earth, we can imagine the Earth is at rest, and it looks like the moon is almost moving in a perfect circle around Earth. What is the force that's instead of string? There's no string attached to the moon. It's that gravitational force from the Earth. So that's another example that could be the cause of uniform circular motion. Now, confusingly, I'm asking here, can more than one force be responsible for causing uniform circular motion? And the answer is yes. Sometimes there are multiple forces. You can't say that there's always just one force that causes it. In other words, in F net equals ma, that F net could be from a lot of forces. So, given that there might be more than one force responsible for causing uniform circular motion, you sometimes hear in books, or students say, they'll refer to m times v squared over r, which we really had in the previous example, right? That's the ma part of F net equals ma. Sometimes people will call that the centripetal force. And that's a little bit misleading because in many cases there won't be any one force that's pointed along the direction that it's accelerating, right? It's possible, and we'll see an example in just a second, that none of the forces points along the direction to the center of the circle. But when you add them all up, you get a net force that points toward the center of the circle, as there has to be if that's the direction of the acceleration. So we never want to refer to m times v squared over r as the centripetal force. We don't want to think of there as being any centripetal force at all. We want to think of there as being a lot of forces that might cause the centripetal acceleration when something is moving in a circle at constant speed. But there might be many forces, and maybe none of them points in the direction towards the center of the circle. But maybe more to the point, this is not the F net of Newton's second law. This is the ma side. And so we don't want to think of the ma side as being a force. When you write down F net equals ma, yes, Newton is saying in a huge variety of circumstances, F net equals ma, essentially everywhere in Newton's world for every object. They're equal, but that doesn't mean we should think of ma as being a force. The force belongs on the F net, or sum of the force parts. And ma we shouldn't think of as being a force, but rather the result of many forces that may be causing it. All right, let's take a break, and then we'll do some more complicated examples where there are more than one force that is causing the acceleration in uniform circular motion.